Alright, testing. Hello everybody, I'll be going over PageRank, the underlying structure, its variants, and methods. First I'm going to introduce what will be covered. So we'll have the background, we'll have paper 1 is PageRank beyond the web, and then we'll have paper 2, fully personalized PageRank and algebraic distribution. In these sections, um, background we will cover what is a random walk, transition matrices and Markov chains, Perrin-Frobenius theory and power iteration, stationary distributions and PageRank basics, and then damping factor and more. These are all kind of required to understand PageRank and the variants I will be talking about later. So in PageRank and its variants, we'll be just going over applications. What is it used for, basically? We'll define the standard, also global PageRank. We'll go over personalization at PageRank and how that can be changes in teleportation behavior. The second paper will be going a little bit more on Perrin-Frobenius theory, because it's important to understand the structure of PageRank, so we can control it. We'll be going into personalized PageRank more, including other stuff as like random restart, node dependent dampings, and what is localization. We'll be getting into applications. So at the end, we can go over some fun applications in chemistry, biology, neuroscience, complex systems, and more. If we have time, we'll be on into what are better methods than PageRank now. Obviously, Google does not use standard PageRank anymore. Higher order random walks, so a lot of big data, high dimensional data, and then embedded representation learning using PageRank. That's kind of just a fun one I threw in. Okay, what is a random walk? A random walk is generalized as a set of steps where each step is chosen randomly, only based on the current position. Therefore, it is memoryless. You might remember this property for a probability in statistics class. You'll see it is very useful for our construction and how PageRank works. Random walks have a lot of applications, just like the aforementioned probability and statistics, but in our case we'll look at using it on a graph, where the graph notation is G is a pair of V and E, where V denotes a set of edges and E denotes a set of edges. So let's draw my graph here. And we're going to put a guy on this node. We'll call him Mr. Surfer. So basically, as referred to a random walk, this is the node we are on. It doesn't really matter if we came from here, 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 here. We're here now, and we can go to any of these 4 nodes with an equal probability, just 1/4. This is just standard undirected, which means this node can visit this node, and this node can visit this node. If you add arrows that indicate direction, then only now this node can visit this node. This node cannot go that way. Alright. Alright, and this brings us to Markov chains. So we can describe the probability of movement between these nodes and a transition matrix P. So then P has some pretty fun properties. Stochastic, which means randomly determined, not predictable. The properties are, as always, square. So same row and columns, and it's always non-negative. So we can have 0 probabilities. We can have, pretend these are 3s. Dot, 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 dot. But we'll never have negative. There's variance. There's row stochastic and column stochastic. So this matrix that I drew is column stochastic because each column sums to 1. We'll be using row stochastic for most, if not all, of the PageRank transition matrix. And basically, Markov chains are a formal random walk that has the following characteristics, which we kind of already discussed. We have these states. We have transition probabilities to other states. So this matrix would kind of be incorrect. Each of these would be actually 0.25. So this guy can go to this one, 0.25 probability. And memoryless evolution. So we're at state I. The probability of moving to state J in one step will look a little bit like this. Okay, here we are. Probability t plus 1 equal to j times t equal to I. So state I to state j, and then if we repeatedly walk, it'll basically look like, and we denote this using pi. So our new state is based on current state times probability of it to visit other states. That's the basics. Perrin-Frobenius theory. So this stochastic matrix has some good properties that help us construct PageRank. All entries are non-negative. We already went over that. This means irreducible, which we would actually call strongly connected. Since this is undirected, each node can eventually visit any other node. That's what strongly connected means, and that's kind of how irreducibility works. And then, yeah, row stochastic. We are computing this, and then Perrin-Frobenius is a theorem we use because it proves that when we're computing pi of t, so we're going to call that our stationary distribution at time t. We basically only need the largest eigenvalue, called the Perrin eigenvalue. Perrin-Frobenius tells us that it exists, it's positive, that dominates all the others, and the eigenvector is unique. Specifically for Markov chains, the largest eigenvalue can be 1. So apply. Okay, let's move on. Power iteration. Power iteration uses parent Frobenius to basically compute the largest eigenvalue. We need it. We know it dominates and it's positive. So basically the goal here is find lambda. We start with a random vector. It can be literally anything. And we repeatedly multiply it. So basically times our matrix, which is the adjacency matrix. Boom, boom. I guess this would be 0 in this case. Anyway, eventually this will look like that formula. The c's are just constants. If we recall dominance, where our max guy is bigger than our second largest, these terms will shrink to 0 as we keep multiplying. And to make sure this converges stably, we normalize the vector we're using. PageRank introduces us to a new notation where the next stationary distribution step, which is denoted by the vector x, is alpha times our transition matrix, P, times the stationary distribution, plus 1 minus alpha v, and then x is usually initialized with our teleportation distribution or just at 0. So that's how standard PageRank is calculated. We will get into what alpha is and also what 1 minus alpha v is, but we've already defined v as the teleportation distribution.